This screencast is on aromaticity, aromatic compounds. Now, aromatic is a term that applies to a broad class of organic molecules. Sometimes it's misused for just benzene, but benzene is simply one of many aromatic compounds. So the term aromatic and benzene shouldn't be used interchangeably. The benzene ring is simply the benzene ring, but many compounds can qualify as aromatic. So to be aromatic, the ring has to have p orbitals on each atom of the ring. It's got to be planar or nearly planar, so benzene's planar, so that there's overlap of those p orbitals. It has to have 2, 6, 10, 14, 18 pi electrons. So it has to meet the 4n plus 2 rule. So benzene has n equals 1 for a total of 6 electrons in the pi orbital. And then it meets all of the rules again because it's cyclic, it's planar, it's got those p orbitals on each atom, it's got the 6 pi electrons, and so it's meeting all of these criterion, and it qualifies as aromatic. But so do a lot of other compounds. For example, there's a lot of heterocyclic aromatic compounds. So what does it mean to be a heterocycle? The heterocyclic ones are those that have atoms other than carbon in the ring. For example, pyridine has a nitrogen. Pyrimidine has 2 of them in the ring. And so this would be substituting an atom other than carbon for a point in the ring. So a hetero or a different atom in the ring. And these happen to be aromatic. If we look at pyridine, we've got the 2, 4, 6 electrons that it's going to put into its aromatic ring. Pyrimidine is going to put these 2, 4, 6 electrons into the ring. And so these are essentially analogs of benzene, and they're aromatic just like benzene is aromatic. So now we're starting to see why we can't use the term aromatic and benzene interchangeably, because pyridine, pyrimidine, these are all aromatic too. And these are called heterocycles for this nitrogen in place of the carbon. We can also have oxygen replace a carbon, but we see nitrogen a lot. We can have fused heterocyclic rings. So here are 2 points of ring fusure in indole, where we're fusing a 5-membered ring with a 6-membered ring. And it's a heterocycle because we see an atom other than carbon at points in these rings. These are all heterocycles, and there's tons of them in nature. There's tons of these aromatic heterocyclic compounds. Serotonin's a good example of one of these compounds. It's a neurotransmitter that's commonly understood as a mood stabilizer. We've seen adenine before. That's a nucleobase, one of the 4 in DNA. And so these are really important biological molecules, these heterocycles. Percy Julian is a famous black chemist who studied alkaloids and studied steroids. And the true alkaloids that he studied have nitrogen in a heterocyclic ring, and they are those that actually originate from amino acids. And examples of those are nicotine and morphine. Morphine, it's maybe hard to see that it's a heterocycle, but this nitrogen is part of its fused ring system here. And this is actually a fused 5-membered ring. 1, 2, 3, 4, 5, 6. Oh, I lied. It's got 1, 2, 3, 4, 5, 6. That fused 6-membered ring. And here's another 6-membered ring here. And so these are fused rings within that morphine structure. It's pretty complex, but cool to look at some of these different heterocycles. So then we're going to look at compounds called polycyclic aromatic hydrocarbons. And this is where we have 2 or more fused rings that look like fused benzene rings. And so here's a point of ring fusure. Here's a point of ring fusure. If we look at naphthalene, Each point that doesn't have ring fusure would have a hydrogen atom. But in order to be able to fuse those, we have to get rid of the hydrogens at those points of ring fusure. So sometimes what we look at is the carbon to hydrogen ratio in these polycyclic aromatic hydrocarbons. And so if we look at naphthalene and we look at the number of carbons, it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With those two benzene rings, we might expect it to have 6 and 6 or 12 carbons, but they're sharing these two central ones. So it only has 10 carbons. And then if we look at hydrogens, there's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So we look at a carbon to hydrogen ratio of 10 to 8. Or if we simplify that, 5 to 4 for naphthalene. We can check anthracene's ratio. And so we'd go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. And then we can check out how many hydrogens it has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so if we go ahead and simplify that, we have 7 to 5 for the ratio there. And again, these points of fusion don't have hydrogens. And phenanthrene rather, should give us the same result as anthracene because it's 3 fused rings. But we can check benzoapyrene. And so first we can check the hydrogens. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 hydrogens. And then we can check our carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So we've got 20 to 12. These are both divisible by 4. And we'll actually have 5 to 3. And now it's a little bit easier to compare benzoapyrene back to naphthalene and see that what is happening is our carbon to hydrogen ratio is actually going down, or the amount of hydrogen is going down. And so with additional ring fusure, we're going to have less and less hydrogen, and we're only going to have hydrogens on the exterior of that molecule. And so as these pHs get bigger and bigger, they will have less and less hydrogen within the ring. So if we think back to PAHs, these are fused benzene rings. So they're fused planar rings, and it's all aromatic. The whole structure is aromatic, and it's getting an increasing number of carbon atoms and less hydrogen. So it's becoming closer and closer to pure carbon the more of these rings that you fuse together in polycyclic aromatic hydrocarbons. So where are these found? Well, we find them as products of incomplete combustion. So wherever combustion is occurring, whether that be a forest fire, a wood burning fireplace, we find it in burnt food, people who are exposed to the products of combustion in a coal-fired power plant. We find them in the products of volcanic eruptions, really any time that there is combustion occurring. If some of that's incomplete combustion, we're seeing that black sooty material, that's often where we're finding those PAHs. And so why are these an issue, or why are we learning about them? Well, they're carcinogens. And the reason that they're carcinogens is because of what happens to them in the body. So they're not water soluble at all. They're only going to be fat soluble because they contain all carbons and hydrogens. So in order to try to excrete them, the body's going to try to make them water soluble so that they can be excreted with our urine. So in order for a reaction to occur for them to be water soluble, it's got to form something like OHs that are water soluble. So there's an enzyme that can catalyze oxidation to add oxygens to the ring so that these diols form that are going to be water soluble and allow the product to be excreted. But the problem is that on the way to that diol, this epoxide ring is formed. And that epoxide ring is really reactive and unstable. And if it happens to find your DNA, it can alter the structure of the DNA and it can produce a cancer causing mutation. And so these are known carcinogens. And that's why we want to avoid excess exposure to the products of incomplete combustion whenever possible. We want to avoid exposure to PAHs in excess. So hopefully now you know a little bit more about aromaticity, about heterocyclic aromatic compounds, and about polycyclic aromatic hydrocarbons.